back. In this section, we'll be integrating functions with a linear input. So, for example, cos of 2x plus 3 needs to be integrated. Now, you do remember when we found the derivatives that the the derivative of sine of x would have been cos. Now, the inputs wouldn't have changed when we found the derivative. If you remember with the chain rule, we would have left the inputs alone as they are, and we would have multiplied by the coefficient of x, or rather, the coefficient or the derivative of x inside the bracket using the u substitution. Now, we are not using the u substitution here. What we are saying here is that uh, we would have ended up with, if we differentiated sine, we would have ended up with 2 cos x. We don't have that 2 here. We only have a cos x, but that's not a problem. We can put a 2 there as long as we put a half in front of the integral. Okay, so that means that now half of the answer to this integral will be half of sine of 2x plus 3 plus c. Simple as that, isn't it? Okay, let's look at the next example. You can make a generalization here that every time we have a linear function inside another function, the coefficient of x will come out at the front, and we, rather than multiplying by the coefficient of x, we will divide by the coefficient of x. Simple as that. In this case, the coefficient of x is 4, and we know the integral of e to the power of anything will be e to that power with the derivative of e in front of it. So the derivative of the function in front of e. We don't have that derivative of 4x, which is 4 in front, but we can put it there as long as we divide by the same derivative. So we can put a 4 inside the integral as long as we put a quarter outside the integral. Therefore, we end up with a quarter of e to the power of 4x as the answer, plus c. I suggest you pause the video and confirm that for yourself before moving on. Okay, one more time. If you see kind of expression here, you simply take the coefficient of the powers of e and you dividing by it rather than multiplying. So we know in this example that integral of sec squared. If you remember, or if you look up in the top left corner, the derivative of tan was sec squared. Therefore, when integrating sec squared, we will get tan. But there is a coefficient in front of x. There is a 3 in front of x. Therefore, we would have ended up with a 3 in front of sec if we integrated tan of 3x. Okay, so let's pretend that we are differentiating tan of 3x. We would get 3 in front of sec squared. This 3 is missing in our integral. That's fine, we can put it there as long as we divide by a factor of 3 outside the integral. Therefore, we will have such an expression which will end up with this answer here. Now I've tried to color code this, and the integral of 3 sec squared is tan 3x. The confirmation is up there. I did that in the first step there. Therefore, we'll have a factor of a third in front of tan, and we put a plus c at the end. Okay, so let's look at the next example. Here we can use u to be f of x here. So whenever we have to differentiate the logarithm, we would have ended up with the the derivative of the function on top of the fraction and the function itself in the denominator. So putting the chain rule together here, we would have ended up with f of x on top of the f, f of x itself, f dash of x on top of the f of x itself. So if you go through the substitutions here and follow the example carefully, you end up with this expression for derivative of log of a function. So we end up with as the denominator, which was f of x itself, and we get this expression. Therefore, from now on, every time we have to differentiate a derivative on top of the function itself as a fraction, whenever you see a fraction where the derivative you have to spot is on top and the function itself is the bottom, you end up with log of that function. Okay, so let's go back and make sure you write this rule with the plus c at the end if there is an indefinite integral. This is a very important rule that I emphasized when I taught the derivative section. You should remember. So let's see this in action in the next example. We have actually 1 on top of the fraction. So, but 3x plus 2 is in the denominator. You think to yourself, what would have been the derivative of 3x? There is a factor of 3 missing to make it work for us. That's fine. We can put a 3 on top of the fraction as long as we put a factor of a third outside of the integral. So, in the end, we will end up with 1/3 log of 3x plus 2, making sure that the logarithm gets absolute signs, and we add a plus c at the end. Okay? Looking at this power of 4 here, we have a linear function inside. The derivative of 2x would have been a 2. That 2 is missing in front of this derivative. So we need to put a factor of a half outside the integral and use the reverse power rule here. So the reverse of power rule says that we need to increase the power by 1 and divide by the new power. Okay? So dividing by the new power and putting a factor of 2 in front of the integral will tell us that we need to divide by 10 because the new power is 5 and the coefficient of x is 2. So 5 times 2 would give us that 10 that we need to divide by. Okay,